15 মিনিট শিক্ষাৰ সমূহ সদস্যৰ হৈ আজিৰ এই অনুষ্ঠানটোত উপস্থিত থকা আটাইকে আদৰণি জনাইছো মই হিৰণ্যনাথে আজিৰ অনুষ্ঠানটো আসলতে আমি চলাই থকা এটা সিৰিজৰ তৃতীয়টো বক্তৃতা এই বক্তৃতা প্ৰদান কৰিব স্যামছাং ৰিচাৰ্চৰ জ্যেষ্ঠ সফটওয়্যাৰ অভিযন্তা ডক্টৰ হিৰক জ্যোতি কাশ্যপে হিৰকক নতুনকৈ চিনাকি কৰি দিয়াৰ কোনো প্ৰয়োজন নাই হিৰকে ইতিমধ্যে আমাৰ এই মঞ্চত কেইবাবাৰো বক্তৃতা প্ৰদান কৰিছে আৰু এই মঞ্চত অংশগ্ৰহণ কৰা শিক্ষাৰ্থী আৰু অন্যান্য অংশগ্ৰহণকাৰীসকলৰ সৈতে মত বিনিময় কৰিছে ইতিমধ্যে আমি আৰ্টিফিশিয়াল ইন্টেলিজেন্স অৰ্থাৎ কৃত্ৰিম বুদ্ধিমত্তাৰ ওপৰত দুটাকৈ বক্তৃতা অনুষ্ঠিত কৰিছো আৰু এই সিৰিজটোত আৰু দুটা বক্তৃতা আছে তাৰ তৃতীয় বক্তৃতাটো আজি হিৰক জ্যোতি কাশ্যপে আমাৰ আগত দিব তেওঁৰ বক্তৃতাৰ শিৰোনামা হৈছে How AI Sees the World ইতিমধ্যে আমি আৰ্টিফিশিয়াল ইন্টেলিজেন্স বা কৃত্ৰিম বুদ্ধিমত্তাৰ সাম্প্ৰতিক ধাৰা আৰু বিভিন্ন ধৰণৰ প্ৰয়োগ সম্পৰ্কে আলোচনা কৰিছো বিগত দুটা বক্তৃতাত আজি হিৰকে আমাক কৃত্ৰিম বুদ্ধিমত্তাই আমাৰ পৃথিৱীখন আমাৰ জীৱনটো কিদৰে চাই বা দেখে সেই কথাটো সম্পৰ্কে আমাক ক'ব আৰু তাৰ পিছতেই এই অনুষ্ঠানত উপস্থিত থকা শিক্ষাৰ্থী আৰু অন্যান্য অংশগ্ৰহণকাৰীসকলৰ সৈতে বাৰ্তালাপ কৰিব সকলোকে তেওঁলোকৰ জানিবলগীয়া শিকিবলগীয়া বিলাক সম্পৰ্কে প্ৰশ্ন কৰিবলৈ আমি আহ্বান জনাইছো এই অনুষ্ঠানটি ফেসবুক আৰু ইউটিউবতো সম্প্ৰচাৰ কৰা হ'ব এই দুটা প্লেটফৰ্মত থকা অংশগ্ৰহণকাৰীসকলেও তেওঁলোকৰ প্ৰশ্নসমূহ চেট বক্সত কৰিব পাৰিব আৰু আমাৰ 15 মিনিট শিক্ষাৰ সদস্যসকলে সেই দুটা প্লেটফৰ্মৰ পৰা প্ৰশ্নসমূহ আনি হিৰকলৈ আগবঢ়াই দিব গতিকে আটাইকে আকৌ আদৰণি জনাইছো আৰু হিৰকলৈ আমাৰ আন্তৰিক আদৰণি 15 মিনিট শিক্ষাৰ তৰফৰ পৰা আৰু আমি তেওঁৰ বক্তৃতাটো শুনো আহক হিৰক
ধন্যবাদ স্যার মোৰ মাতটো শুনিছেনে ঠিকে
শুনিছো
সকলোকে ধন্যবাদ প্ৰথমে এই বক্তৃতাটো শুনিব অহাৰ কাৰণে স্যাৰে এনে ইমান ধুনীয়াকে আদৰণি জনোৱাৰ কাৰণে গোটেই 15 মিনিট শিক্ষাক মই ধন্যবাদ জনাইছো আজি থাৰ্ড মানে লেকচাৰটো হ'ব সো মই ইংৰাজীতে কম আপোনালোকৰ যদি কিবা কোৱেশ্চন থাকে বা কিবা বুজি নাপায় চ্যাট বক্সত লিখি দিব মই বক্তৃতাটোৰ শেষত গোটেইখিনি কোৱেশ্চনৰ আনসাৰ দিব চেষ্টা কৰিম তো মই আৰম্ভ কৰিম ইংৰাজীত So today in the previous lecture we saw how the robots interact with humans or our living world and how AI has been used to empower the robots to operate among ourselves within humans. So today we'll look at on the one aspect of like how to make those AI robots. So most of these AI or intelligent agents that need to operate in the real world needs to first perceive the real world. Perceive means they need to understand where they are and what the other entities surrounding them and how to interact with them. So for that, vision, like how we see, is the main or a major form of perception. So, and that is where I also did my studies during my graduate school. So today I'll talk about how AI in the current technology domain, at least, how AI perceives the world with the camera feed, basically, since we humans use the eye, but the machines use the camera. So how these intelligent systems or the algorithms understand what it sees in the camera. So before going further into it, I would like to demonstrate like what is the current state of the art in the AI systems. So this is a screen capture from a autonomous vehicle built by Tesla. So Tesla is one of the autonomous vehicle or electric vehicle companies that are also making autonomous driving systems, and they have been working on this kind of systems from like almost a decade or more. So their systems are very how to say, at the top of the current capabilities of AI. So I think it's a good reference of what AI can do currently, or what AI sees currently. So,
Hirak, we cannot see your screen. Like it just says loading.
oh, what about now?
1 second.
Do you see the video feed?
No, no. Oh yeah, now it is there. Yeah, now the screen is there.
Oh, but if I play in slideshow, you do not see the video, right?
Yeah, you can try again. That.
Or otherwise, I'll just run it in this mode.
Oh yeah. Okay. Thank you.
Can you see now?
No, just a blank screen.
Okay, maybe I'll just run it in this mode. Is it fine now?
Yeah. Yeah.
Okay.
Now it shows.
Yeah, this is how I'll do them.
Okay.
Sorry.
Thank you.
So yeah, sorry for the interruption. So yeah, so this is the Tesla self-driving system, and you can see while it is the car is moving forward, the cameras, there are like multiple cameras, and this is just a view of like accumulating all these cameras like one view. So at like in real time, this autonomous system is calculating all these like what other cars are in front of it, the stop signs, or the in the street, the lane markers, and human, and all those. And also you can see these tags here, and there's I hope you can see, but there is like a number associated with it. So that number tells like the distance of that particular object, maybe like a vehicle or a human, from the car. So, and it does all this in real time. So, and this particular company called Tesla, they only uses camera, so they do not have like radar or like other sensors. So all you see here is obtained using like 5 or 6 cameras mounted in the car, and this AI system is perceiving like human, pedestrian, other cars, or all of them in real time, and you can see how good it is. So yeah, it is not perfect. So like in the last lecture, Tiffany told us about this level of automation. So it is not yet level 5, that means fully automatic, but still at the perception side, it is still there are still things to be done, but it is quite good. So this is where we are. It is not yet perfect, but it can already like recognize most of the things in real time that we see in the world. So today we will basically go in a bit deeper, not too much technical, but still to understand how these algorithms are understanding all these objects that are available to the camera on the scene. So the main agenda would be, first I'll talk about a few, like not few, the most important problems in computer vision, and how AI-based algorithms has been used in the recent years to solve these problems. And then I'll also talk about some challenges, and I'll briefly mention some of the resources that you can look for to start like playing with these data sets, or start exploring computer vision with AI algorithms. So this is the most common problem. Given an image, what this image is, like what is the main character, or what is the main feature of this image. For example, this is, if I show you this image, this all like all the images in the first row, all of them are images of airplane. Although they might have some other objects, still the primary focus is the airplane. So the image classification is the problem of identifying what is the main object or the major feature in the image. So that is one of the main problem in computer vision. And then another problems, particularly when we go to like robotics kind of applications, we not only just by knowing what is there in the image, that's not enough. We need to know where the object is and which area in the scene the object is occupying. So beyond classification, there is another problem called localization, like localizing where in the image this particular object is, in this case this cat. And then detection is similar to localization, but detecting like multiple objects of different categories. Like in this one, there is a cat and a dog and a duck. But you can see in both these cases, there is just this bounding box, like a rectangle that surrounds this object. So this is fine maybe for robotics kind of application, like self-driving car, because most of the objects are far away. But for example, you are using this kind of detection algorithms for figuring out in like a scan of the MRI scan of the brain, you are trying to figure out a particular region in the brain. Then this kind of boxes are not enough, because these regions are not rectangular and you need to know the exact finite pixels that the object is occupying. So that problem is called segmentation. So in segmentation, instead of drawing a bounding box, you draw like the exact contour that the object occupies in the field. So that is important also in many applications, like in medical image processing and those. So those are important ones. And then again, coming back to more like robotics kind of application, there is this problem of tracking. Tracking means users give any visual feature. For example, here, it will draw a bounding box across this person driving this, riding this bike. So yeah, so it draw this box and labeled it as a motorcyclist, and then this another box across this pedestrian. And then in the video, as it tracks from frame to frame, it will keep on updating those bounding box to reflect the current position. So that is called tracking. So see, now the video is playing, and this bounding box for the pedestrian red colored and the yellow colored bounding box for the motorcyclist, they're being updated every frame during the video. So that is the problem of tracking, and it is very important in like robotics kind of application. And also not only robotics, like for example, in missile technology, where they have this guided missile where there's a set a target, or anti-missile system like that are used to deflect targets. So in those cases, the AI system need to calculate the target location and update it in real time. So tracking is that problem. Sorry, moving ahead. So, and then another problem is called depth estimation, which is very simple. Given an image, what is the depth of different objects? Maybe I should show you. Yeah, so this is another self-driving car video, and as it moves down this street, so bright region means near, like low, like less depth, and dark means more depth. And this is like a colored representation, but you get the idea. So in this kind of street, these are probably cars that are parked next on the street, and these are trees, and these are like far away. So estimating depth from a single camera is a tough problem. From two camera also, it is tough if in like a natural environment. And one final problem that is very important in robotics or in AI application is motion estimation. So given a video of like a moving camera, it is to calculate how fast or which direction the camera is moving. So you need to calculate that in order to first to know how, like the camera velocity, as well as that is needed to calculate the object velocity. For example, in the self-driving car scenario, you already know how fast the same, like the car is moving, the same car. So But in other cases, that kind of information might not be there. Then you need to know how fast the camera is moving in order to calculate the other moving objects. So these are some of the most important, and I would say the tough problems in computer vision that needs to be solved. And most of these that go into like robotics kind of applications, like tracking or depth estimation or motion estimation, those need to be calculated in real time, because the AI system interact with the environment in real time. So those are constraints. So I'll now go into like how AI systems have evolved over the years to tackle some of these problems. I should not say before these AI systems, there was no solution to these problems. It is not like that. Even before that, there were logic-based solution, like fixed algorithms, like definite algorithms, where you always get the same answer. So logic-based. So then what happened? The accuracy of those algorithms were not, I would say, not perfect, like they were not highly accurate. So in the quest for increasing the accuracy of these algorithms for computer vision, people started looking into AI. So what is the difference between logic-based and AI? In logic-based, you just need to make or design the algorithm. You do not need to have data to like any sort of training. Is like the same fixed algorithm work on every new data in the exact same way. On the other hand, in case of AI algorithms, you need to first train the AI system with some training data. For example, I want to make an AI system that can segment or that can classify, for example, skin cancer images. So for that, I need to first gather like 10,000 or like even more, maybe, to make it more accurate. More data leads to more accuracy. That many images to train the AI system. After the training is done, then we have an intelligent system that can predict whether a new image of the skin has skin cancer or not, like a doctor, or like an expert, to some accuracy. Like I'm not saying it will always be accurate like a doctor, but for the most part. So like that is the goal. So that is the difference between logic based and AI based, because that means we need training data. So one of the first then the current AI based system that are the most successful ones are developed using an algorithm called neural network. So the first neural network that was developed for this kind of vision applications was called LeNet. It was developed in 1998. So it was developed to recognize handwritten digits. Actually, this image is a character, but it was initially made to recognize digits. And as far as I know, it was used by the United States Postal Service to read the zip codes automatically to sort the mails that go through. And then later it was used for still used for reading checks when you submit a check to the ATM machine. So anyway, so how it works, since today is about like how AI sees the world, I want to give like a brief idea about how it works. So given image like this, so this is an image of a character A. So what it does is it processes this image in multiple levels, like iteratively. So first, in the first level, it divides this image into smaller patches, like small regions. So for example, this image is divided into 10 by 10 regions, like sub-regions. And then each region would be processed through some sort of, they call it filter. Filter means, a filter is a feature detector. So there can be a filter that looks for an edge that is in the horizontal direction. Then there can be another filter that looks for an edge in the vertical direction, things like that. So the system is basically trying to look at this image like we human do. So if we had this character A written differently, you would have looked at that particular edge somewhere. And this AI algorithm is trying to do exactly the same thing. It is trying to look at like a local region, how this feature looks like. Then once the first, so in the first layer, there can be, in this case, I think not many feature, only 6 features are being detected. And then in the second layer, then there would be more features. So then this is like something called pooling, to like reduce the size of the problem, to make the problem simpler. In the second layer, there would be, and this process is called convolution, the feature bank. So the convolutions look at, again, out of this, whatever feature was detected, it looks out at those features again, pixel by pixel, in like a local region. And it does this convolution operation in multiple steps, like iteratively. And after it does those things, at the final step, it has some computational unit, or they call it neuron, that gives the probability whether this is a character, or this is like an A or B or 1 or 2 or 3. So so that is the overall idea. And to make this AI system recognize this later as A, it needs to train the system with many examples of like handwritten digits or handwritten characters like this one. So at the beginning, it will not be, like there is no predetermined or human designed algorithm that is already there. It's not like that. It's at the beginning, it cannot predict what this is. It just sees some pixels. But over time, during training, it learns to recognize that this particular feature, or this group of features, constitute an A. So that is how it works. And after training, you do not need to train again. Users can give new data examples, and this model will be able to predict whether that character is like A or B. And just to, so like, I'll not go into all the math, but just to tell how it works. So the training, I mean, so in the training, users give, like I just said, you need to have like thousands of examples, right? So you present an example to this AI system, it initially predicts some random prediction, like it maybe at the beginning, it predicts this as a D. So that is an error, right? So then this error is sent back towards all these convolution functions, and these convolution functions are updated with that error metric. So, and if it predicts A for this one, then there will be no error. If it predicts something else, then there will be error. And over time, as we train it with more and more examples, it learns to make these correct predictions, and this error goes down. And we stop the training when there is like no error or very little error. And this algorithm that is used to train this kind of systems is called backpropagation. I'll not go into the math, but yeah, the idea is what I just explained. You present an image and you calculate the error, and then you change all these convolution functions with that error. If you have questions, we can discuss this at in the Q&A. And then you can see this, sorry, how many convolutions are there? 1 convolution layer, 2 convolution layer, and 2 fully connected, like different types of connection, but total 4 layers, right? And actually 1 more, so 5 layer. But people then figured out, if we make these AI systems with more and more layers, as we add more layers, this system become more accurate. So initially the LayNet I showed you, it was yeah, it was just tested on, as I said, just digits, so 0 to 9. So it had to only identify if the digit is 0 or 1 up to 9. That's it, only 10 classes. But if we want to use it for something like in the real world, like if you like capture a photo with your phone, can I use it to detect if there is a person or if there is a dog? So those kind of problems are much tougher than compared to like just those A, B, C, D kind of, or 0, 1, 2, 3 digit recognition. So people figured out that in order to do those like complex problem or recognize those complex objects, you need to have deeper, like much deeper neural networks. So in order to do that, someone like called Alex Krzyzewski from University of Toronto in 2012, he developed like a, how to say, it's a modified or extended version of this LANet architecture, and he made a network with 8 layers. And with that network, he was able to, and then there he also used like another kind of computer called graphics processor. So it's the kind of processor we use to play computer game. So he found a way to instead use those to train this kind of neural networks and execute those. So with that, he was able to build this network with 8 layers, and it is able to classify 1000 classes. So not just digits 0 to 9, it can classify human, or in this case, this is an example for hammer. So they used it on a dataset called ImageNet, and these are some examples of the class or the category called hammer. And you can see so many variations of hammer, right? Hammer pointing down, like the image pointing downward, or it is pointing towards the hammer, like all variations. So even with all these variations, this model was able to predict what if this image contains a hammer or, for example, a human. And as I said, people found out that if we add more and more layers, these AI systems become more accurate. So in 2012, with 8 layers on this ImageNet dataset, they were able to get accuracy of 16.4. It's the error rate. So like lesser the error, it's more accurate or better. So in 2012, it was with 8 layers, the error was 16.4. And as you see, as the years went on, 12, 13, 14, 15, 2015, the number of layers kept on increasing. Maybe not in 2013, but in 14, it became 19-layer network called VZZ. In 2014, another network came with 22 layers, and then another with 152 in 2015. And as we increase these layers, this accuracy or the error rate dropped or accuracy increased. So in 2012, the error was 16, and 2015, it was 3. So that was quite an achievement. So that led to kind of the rapid progress in AI that you now see. All the companies began investing in AI, and all the governments became more focused on like developing AI research facilities and so forth. So because of that, I think now there is a lot of effort to make these systems even more better, and also use them in real world applications. So that was just image classification to know what is there in the image. But as I said, if we want to use the AI in for example, robotics application, then we need to also know where the object is. So for example, we put an AI in a robot, and the robot needs to track a dog, for example. So it needs to know where a dog is, and as the dog runs, it needs to continuously update the location of the dog. So for those kind of applications, we need to first do object detection, to detecting in the image which part of the image contains the dog. So people then figured out a way to, how to say, reassemble these parts that we just discussed before, to make it an object detector. So what it did, and this is the earliest approach. I'm just showing you this so that you know the overall idea. So they divide this whole image into, they call it region proposals. So like multiple regions of random shape. They're all rectangular. I mean, random size or random locations. So they, from one image, they generate this kind of up to 2000 bounding boxes like this of a different size or different location. And then for each of those, image region or region proposal, it would run what we just discussed, the image classifier AI. So for each bounding box, then it would know if that bounding box contains a human or a horse or like something else. So this is the first object detector that was made using AI called RCNN, and it was very computationally expensive. So people have worked a lot over this, but overall this is the idea they built upon, and now they are quite faster. And currently they are used in many robotic systems. These are some of the examples. So this graph here on the sorry, on the x-axis is the time, like how costly to run this algorithm. Can this algorithm give me like the result instantly, or does it take 1 minute to tell me the different bounding boxes? So you can see if you need better performance, these algorithms also need more time, like more time in the sense like it will have more layers or bigger or more complex layers or bigger size. So because of that, the computational time or time it needs to detect these objects increases, but the performance also increases. So the goal overall here is to go on the left side of this graph as much as possible and go to the higher end. So top left is where we are aiming at, right? So top left is like low computational time and high accuracy. So you can see it's always this trade-off going away from it. And these are like some of like few of the algorithms. So the mobile net one on the top left, this example, you can see these bottles on the table were not detected because this mobile net is a small network and it's not very accurate. Against that, this ResNet 101, this is a very big network, and you can see all these bottles, cups on the table, all of them are detected well. So that is the trade-off. So if you need fast performance, you go with like smaller models, but then you lose some of these detections. If you need higher accuracy or if you want to detect everything, then you might have to use more computation. So the research that people are doing nowadays is to lower the computational time while keeping or maintaining the accuracy. And then for segmentation, so this is basically extended this kind of work. So before that, what is the difference between detection and segmentation? I'll just briefly explain again. So this is a chest radiography, so hearts, lungs, and some this bones, I guess. So given this kind of radiology image, you want to like segment out which part is the lung or which part is the heart. For example, for the AI to give a preliminary screening on some disease, for example, then you need to segment those organs part like pixel by pixel accurately. So then you cannot have like a bounding box like this kind of rectangular shaped boxes, but you need to have pixel accurate classifier, it's basically a classifier for every pixel. And then in other cases, like you probably want to identify which part, because these two persons are just sitting next to each other, their bounding boxes will have lots of overlap, right? So we want to figure out exactly which pixels is like this purple person versus this yellow person. Then also you need segmentation. And they kind of repurposed the RCNN architecture and made something called mask RCNN. So what it does, on top of what predicting the bounding boxes like the previous algorithms, it also predicts for each bounding box a mask. A mask meaning it's another layer that says this pixel has the object versus this pixel doesn't. If the pixel, for example, this dog here, for the mask image of the bounding box, the pixels that lie on top of this dog will be 1 versus all the background will be 0. So it's a binary mask. So this algorithm just does that. On top of predicting the other things like bounding boxes, it also predicts a mask. And then it just generates this kind of segmentation images. And finally, so all I said was using lots of data, like training using lots of data, which is not ideal all the time. For example, this segmentation, this kind of AI system, if they need, for example, 1 million examples, so some person or some human need to prepare those 1 million examples. Like they need to draw this like the edges of this elephant or edges of this person in 1 million examples. So that is a lot of data. So I'm not saying people are not doing that. People, for example, in China or in like many other countries, there are labs set up where like thousands of people work every day to basically draw these contours or these edges for these objects of interest. So, but yeah, you can imagine if we employ 1,000 person, then it's a lot of resources, right? Monetary or time. And for example, this kind of this is a easy example, I would say, but if, for example, in the MRI or in the scans of the brain, those regions are very tiny and you need experts. You cannot just employ anyone to do those kind of leveling. And then for expert levelers, for example, doctors or more practitioners, then it is even more costly. So you cannot always afford this kind of supervised, they call it, like when this training is needed, you cannot always gather this many training data. So how to like circumvent that? So people actually not now, this is an old trick. I mean, people have been trying to develop algorithms in AI that do not require any leveled training. So for example, they just learn from any image that they can just get in the internet or anywhere without any sort of like labeling that this is a human, this is a dog, those kind of level. So these are not, I'd not say they are the state of the art, like they're not the highest most accurate compared to this kind of training setup kind of algorithms, but the effort is to make these unsupervised methods that do not require training as accurate as the ones that require training. For example, then we would not need so many doctors to label all those brain scans, right? So that would be great. So that is the effort to make those accurate. So this is one example, and you'd see this is not as accurate as this mask-R CNN, which is, you can see very accurate pixel level. But this is unsupervised without any training level, but you can see they're improving, I would say, and like getting closer. For example, this skateboarder, this is the segmentation. So probably not very accurate, like this rails are not continuous, but still it's getting there. So this will be a really big help for people who can, for example, this kind of medical applications, and also if you do not have a lot of time and money to gather all those training data for like a real world application. Finally, so I talk about some of the challenges that are there in AI, in applying AI to computer vision. So the main first challenge I was just mentioning is the supervision using data for training. So take this example image. It has, you probably want to identify the segmentation for each of these banana or these berries or these carrots, right? So imagine hiring some person to label all these pixels one by one for each of these vegetables or fruits. So that would take a long time. So that is basically argumenting for unsupervised methods that do not require training. So this kind of situation demand that you develop an algorithm that do not require like labeling all this, because that will consume a lot of time. So supervised data is a hassle, and then just not only that cost and thing, but then as I said, you employ 1,000 person to label a data set, then each person will have their own nuances or differences, so that like the labels will not be consistent, right? So that might cause problem or accuracy problem when you actually use it. And then there'd be subjective. For example, you have a brain scan, or you have a like there's a tumor data set, and you employ 1,000 practitioners to like segment those, or just mark those whether those tumors are cancerous or not, just by looking at it. Probably it's difficult, but yeah. So, and everyone will have their own opinion based on their experience, so then it leads to some subjective bias. Then there'll be also privacy issues, like yeah, a lot of from images, a lot of like untold things can be discovered, which maybe not expected by people, like from which these images are collected. So then there is a violation of privacy as well. And so that is the first main challenge of AI-based vision. And the second main challenge is the computational requirement. I showed you AlexNet in 2012 broke this like really like introduced this use of AI into vision. And then since then, so this on the x-axis are those years since then, 2012, and on the y-axis is how many more computation cycles these algorithms are using. And you can see as this as time goes on, these algorithms are becoming more and more complex, requiring more and more operations. And just keep in mind the y-axis axis is exponential, so it might not look like a huge increase here visually, but it's a lot. It's an exponential factor. So yeah, so that is a problem. Particularly this red ones. It's a new type of model called transformer, which I did not discuss today, but actually the unsupervised method I showed you uses transformer. Anyway, so that those kind of algorithms are, the number of computations or complexity are increasing even higher than this like convolutional neural networks. So that is making kind of hard for independent researchers or like small schools to compete against, for example, big corporations or big universities with lots of resources to develop new algorithms. So that I think is a challenge. So we cannot just keep on increasing this resource requirement exponentially all the time. We have to somewhere limit that, and somewhere try to find out better ways to solve this problem with the same accuracy. And not only that, this also leads to a lot of energy consumption. So now the focus is to go green. That means to use less and less energy. But all these algorithms are going on the opposite direction entirely. So we need like now I think many megawatts of power to train one of each of this model, which is not ideal. And like a small university, for example, or research lab cannot probably afford to use all those. Then one algorithmic challenge is something called adversarial examples. So adversarial examples is like AI itself. It's a problem manifested by itself. They found a way to trick this kind of models or the algorithms I showed before. So this is an image of a panda, right? It's an animal in China. So initially, the AI systems, the state-of-the-art AI systems would recognize this as panda. But then we add some noise into it, then it still, to me and to you, it still looks like a panda, right? But this model fails to recognize this as panda after adding this noise, and it now calls it a gibbon. It's a monkey. So that is so that what does it mean? So people can try to come up with some specific noise pattern that change the recognition of this AI system. For example, there is a human identification AI system, for example, and someone uses a noise, and then now my image is recognized as someone else. So that can be potentially a problem. For example, there are many buildings where when you enter, or security kind of like facilities, when you enter, they would like do a face scan, and then or like a biometrics, and decide whether you are the person entitled to go in or not. Then someone can just fake another image and put it on their phone, and then like fool this system and can still get access. So those kind of problem. And many of these convolutional algorithms I discussed, they suffer from, this is just one example of rotation, they suffer from some sort of distortion. So rotation is like the most easy one, let's say. So if you rotate this image by a little bit, this vulture is now recognized as an orangutan. So yeah, you can see rotation has a big impact, and that potentially, but it's not that critical to like use it or customize it for like a security threat, but still it can fool the AI system. And then again, yeah, this perspective of the, or like same object from all different perspective looks very different. So the photographer can, or like whoever is trying to trick, then they can just present a different view and trick the AI. So the challenge here is basically to make this AI system, the new AI models, robust to any kind of this kind of trickeries, so that this AI can detect that this is still a panda, this is still a vulture, and this is whatever the hot dog, instead of this false fake categories. So this is one example. So I hope you can hear the voice. Let me know. So this is the video itself originally was there of Mark Zuckerberg, who is the founder and CEO of Facebook, or currently Meta. And then this deepfake is one kind of adversarial where they change the voice of that person, or also the image, to appear like he's saying something that he was not actually. So, and it's very hard to actually get that. I hope you can
Imagine
hear.
this for a second. One man with total control of billions of people's stolen data, all their secrets, their lives, their futures. I owe it all to Spectre. Spectre showed me that whoever controls the data controls the future.
I wish I could tell you that we're going to be able to stop all interference, but that just wouldn't be realistic. There will always be bad actors in the world, and we can't prevent all governments from all interference. But even without our employees directly involved in the sales, we
Imagine this for a second.
now I'm not
One
gonna
man
sit here and
with
tell you
total
we're
control
gonna
of
catch
billions
all
of
bad
people's
actors.
stolen data. All
We
their
don't
secrets.
So on the left side of the screen is the original video where Mark Zuckerberg was telling about some data privacy issues with the governments. But on the right hand side, it is totally fabricated video with him saying completely different things. And
People say it before they
lives,
say it.
their futures.
Frankly,
I owe it all to Spectre. Spectre showed me that whoever controls the data controls the future.
yeah, so you can see it's quite believable by now, this kind of adversarial examples. So while the AI community kind of came up with this kind of systems, there is also effort going on to detect whether a video or an image is a real or original image or video versus something created by AI. And yeah, that can potentially lead to a lot of issues in our society. So that is very important challenge, I think, for AI to solve. And that's it for this lecture. And I would say for regarding the resources for computer vision in AI, there is a lecture by, I would not give link here because it's I mean, it's better probably to just say it out, or I'll probably write it in the chat. So there is a Stanford University class on image understanding. I think that is quite useful to learn all these concepts from basics. And then there is a computer vision book by Richard Chalecki. So I'll post the link on the chat soon, and then you can follow those. And to learn this or to use these AI models regarding vision and get the data sets, you can just go to PyTorch or TensorFlow. Like their repositories, code repositories, and they have examples of different kinds of AI models that are already built. Or they have tutorials of how to train those as well. So this is it for today's lecture. In the next lecture on February 5, Professor Jugal Kalita will talk about natural language processing. So with that, I'll conclude my talk today. If you have questions, just let me know. Either write it on the chat or just you can also like speak out. Thank you.
Thank you, Hirak, for this excellent talk on AI, and basically it's like the other side of the story, how AI sees the world and how like the AI models are processed or designed, and what are the challenges. Thanks so much. Let us see if there are questions in the chat box. So here is a question from Shishir. So Shishir, I will unmute you. You can ask it directly. 1 second. Give me 1 minute. You can unmute yourself now. Please go ahead.
Hello.
Hello.
Hi. আপোনাৰ ভাল লাগিলে very interesting and like very informative. মোৰ এটা সৰু প্ৰশ্ন আছিলে মানে can you give some ideas on the explainability of AI models, like whatever the prediction we have from the models, so especially from the for the medical computer vision applications. I mean, like why and how behind an AI model's decision, like why models predict and like how it predicts, because especially for imaging, medical imaging applications, so if we can assist the doctor, like why actually I predict like some tumor is there, and that way like we can assist that, like some issues are there, but I predict for that reason. So can you give some idea on that? Thank you.
Yes. So I just posted something on the chat. So this is a link to some of the methods that people can use to look at which image locations the AI model is using to make a prediction. For example, can you see? Yeah, I think it is shared. So to classify this image, for example, this is probably a dog. So you can so this method called guided backpropagation, you can use that on a trained model to highlight which features in the input image were looked at by this AI model to make the decision that this is a dog, for example. And for human, for example, here, yeah, this person here is not occupying a lot of area in the image, but you can see here it's not very visible maybe, but you can still see some of the features of the human. So likewise in the medical imaging, you can use guided backpropagation. So what guided backpropagation does is on a trained model, when you use it, it just look at where the gradient is flowing. So for the winning class, for example, your neural network has two classes. Tumor is benign versus non-benign or cancerous. So suppose the model predicted it as cancerous, then you can go to the cancerous neuron at the last layer and then just backpropagate the gradients from the same input, and then at the first layer you will see this kind of features come out. So if it predicted as non-benign, then you can look at whether the model is actually looking at the tumor cells or not, or just like looking at somewhere else. So that is one way to look at where the model is, like what the model is looking at to make this particular decision. And guided backpropagation is just one, but there are other also. I forgot the names, but there is another method that gives you the image patches that the model was basically focusing on or attending to. It's kind of an attention mask if you're familiar with that, but you can use those as well. Yeah, I think this slide that I just mentioned has good explanation of that. Did I answer your question or have more doubt?
Wait, I think I have to unmute Shishir again. 1 second.
Oh, he said thanks. I think he understood.
Yeah.
Okay.
ধন্যবাদ.
Yeah.
ঠিক আছে, ভালে. Okay. Thank you.
আৰু এটা প্ৰশ্ন আছে Bisakha Bikhya. So Bisakha, can you please unmute yourself?
So I have a question. Sir. Hello,
Yes.
am I audible?
Yes, you are.
Okay, so as you have told that the CNN has very much, the more we increase the number of hidden layers, the more the accuracy will be there. So can it lead to an issue of overfitting if we increase the number of hidden layers?
Yes, I mean, not always. Depends on the data set. So if the data set is small, like that disease data, sorry, not the handwritten disease data set, that is a small data set of just 10 classes. So if you put a very big model there, then the model will be basically overpowered for the data set, and it will lead to overfitting. It will memorize the whole training data, right? So overfitting is for the others, overfitting is the situation where the AI system basically memorizes the whole training data set to make like 100% accuracy on the training data. But problem is that if it does that, it does not learn like general concepts. So when a new testing data comes in, it fails to give a good accuracy. So that's the problem of overfitting. So Bishakha's question is, if we make the neural network too powerful by adding many layers, does it lead to that kind of situation? That means it memorizes the whole training data. So that depends on how big the data set is. If the data set is small, then yeah, it can lead to overfitting with a big model or complex model. But if the data set is very large, for example, ImageNet is like more than a million images in the training set, so it's hard to overfit. But yeah, so it can lead to, so the, yeah, it, and then yeah, so it depends, as I said, it depends. So how to make sure that it is not happening? So during training, you should set aside the small part of the training data set for validation. Validation is kind of testing. It's like you train, so you have for example, you have 100 training images. So you train the model on 80 images, and then on the rest 20 you do not train it. After every cycle of training, you look at the performance on the 20. If you see the performance on the training set, the 80 images is going up and up and up, and the performance on the 20 images is like saturated, or it's not going up anymore or going down, then that is overfitting. So you should stop the training as soon as this validation set performance saturates or goes down, so that you make sure that the model is not trying to memorize the training set. So that's the overall idea. And then so that is more like basic like general machine learning concept. But in for example, in neural network, there are like more algorithmic ways to prevent it, like using dropouts or using normalization. Then those kind of like methods also make sure that overfitting doesn't occur easily. Yeah, did I answer your question? Or
Bisakha, you can unmute yourself if you have something to add. Oh yeah, you can go ahead.
yeah,
Hello,
you
am I
can.
audible? Am I audible?
Yes.
Okay,
You are.
sir. I got the answer of the previous question. So another small doubt I have, like, sir, can you, sir, give some examples of the present ongoing projects on, especially on convolution neural network that is going on, sir, so that we can, work on it.
Oh, going on, you mean oh, you mean in any particular lab or a particular problem you have in mind?
So actually, I just want to, I'm just a beginner. Like, I have just studied the CNN, not in depth, but sir, I want to, opt for some projects, like, so that I can understand this more. Like, so some personal projects or some projects that in group or in laboratory that might be helpful, sir.
Yeah, I mean, yeah, so in like all the problems I mentioned, like I think image classification is kind of saturated now, but people are using something called transformers. which is a bit more complex and advanced model of like CNN. So transformers is the current trend as far as the architecture goes. And for problems, unsupervised or self-supervised learning is a big problem now. And then again, the adversarial robustness, like make the AI robust against this kind of adversarial attacks. That is another very important theme going on. And then again, in all these other problems I mentioned, depth perception or object tracking or object detection, none of these AI systems are like 100% accurate. There is like, if you go to like a conference website called like any conference website in vision, like CVPR, computer vision or pattern recognition, I'll put the links here, or ICCV, you can go through the proceedings of what this like latest papers are doing. In computer vision or in computer science, most of the latest research come out in those premier conferences. So the best location would be, I think, to go to these conference websites, and because all these papers are freely available. And then look at what this last year's conference had, like what are the papers were on, and then look through, because it's a big conference, they would have someone working on like all the problems I mentioned. Then you have to pick and choose like which one interests you more, I think. So yeah, and usually what gets into these conferences is the state of the art, that is like the top currently there. So yeah, if you want to improve or like add anything, then you have to basically beat those papers. So that is a good place, I think, to start. I'll put the link for the CVPR archive here. And also, yeah, so neural networks itself is not only used in computer vision, it's also used in other problems, right? Like natural language processing or even industrial production or automation of like, how to say, the insurance industry, they use it a lot, banking industry, they use it a lot. So the AI is kind of developing, the algorithms for AI is developing not independently, but it's also, you know, developing outside of computer vision as well. So for that, so there are two things. If you want to focus on computer vision, then you should look at computer vision conferences. If you want to focus on algorithm improvement, maybe you should also look at like machine learning conferences like NeurIPS or ICML. Yeah, again, the same approach. Just look at their recent conference proceedings. So that's the best place, I think. So I'll just put the link for CVPR papers, and you can also find the ICCV and other papers just by like going to their website. And if you, yeah, so then again, this is for like top state-of-the-art research. If you want to learn something, I just like learn all these data sets or all these methods, and I think the best location would be this GitHub website I just put on the comments for PyTorch. So they have a repository of all these models and all these data sets. So that is the good place to start, and some of these books and the presentations I mentioned. Sorry, someone asked something.
Yeah, there is another question. Drishtiran Saikya, you can go ahead and ask yourself.
Hello, everyone. Am I audible?
Yeah.
Yes.
Yeah.
Yeah. So as Sir mentioned that there is trade-off between the latency and the accuracy of ML models. So like I wanted to know by his context of latency, like did you mean the latency due to this complexity of the ML models, or like you meant other part of computer sciences such as like the CPU architecture or other aspects which could generate latency or the limitations of hardware, etc.?
Yeah, in this case, I just mean the complexity of the models. For example, more layers or more flops or like more operations lead to more latency. Or I should say probably more than latency, throughput is the more concern here. But yeah, also latency. So Yeah, and yeah, I think the hardware design also contribute to that. For example, if you run it on a CPU, it will be more, it will take more time to get the result against like a GPU, or there is like neural processors specifically designed for AI models. So those will have even like less latency and higher throughput. So, but yeah, so what I talked about is mainly from the algorithm point of view, yeah, yeah, exactly, like with hardware that are more designed or oriented towards AI application, they're definitely better. And yeah, one easy way to get access to those using maybe Google Colab, where Google provides access to like GPUs and also like tensor processors.
Okay, yeah, I absolutely got it. I have another question. In the industrial context, so like are the whatever the products are being made or whatever AI research is being done, are there like close coupling or close integration between the two, like the AI researcher team, software engineers team, as well as the hardware team to build a product as a whole? Or like are
Yeah, yes. Because yeah, that's a great question. So yeah, again, depends. So if it is a product, like for example a phone, or like a TV, something that go like a where you are selling both the hardware and the software, then to make sure that the hardware, because the hardware has limited resources, right? Like each SoC design, I hope you're familiar with all those. So as like the computer architecture design will have like limited budget for display, or limited budget for, I'm just, maybe phone is a good example. It has a camera, it has a display, it has a communication, all those routines running all the time. So each of these modules have like limited budget or limited amount of time they can get access to those. So if you're suppose making an app to like improve the picture quality of the camera using AI, then you only have so many, in case of associated call in terms of gates, like how many gates are there. So you only can get access to this many gates or this much time in the cycle. So there need to be some yeah, the models need to be designed so that those hardware requirements are made. So yeah, when you're designing or selling an overall system, then you need to take care of that. So I work in Samsung, so we make devices, products, right? So we need like hardware, software, we need to look at it from like, yeah, from the whole overall system performance perspective, not just accuracy, but also like the time it needs or the energy it needs, those kind of stuff. But if you're suppose working on a cloud kind of system, then you probably I don't know, have like infinite availability of resources, then I mean, then you probably don't need to care much about like the hardware constraints that much. So yeah, it depends on the product you are working on.
Sure, yeah, got it. Like I have another question, last question. So like as you have both experience of the academy as well as the industry, I wanted to know that like how for a particular challenge that you encounter in academy as well as the industry, what is the difference in approach, or like, yeah, basically what is the differences in expose and what has been your experiences in either of them? Yeah, in both of them.
Yeah. Yeah, I think in academia, it's how to say, at least I think in academia it varies a lot. Depends on I think depends mostly on the professor, the person, the PI running the lab. So some professors are willing to give you freedom about what project or what kind of problem you want to work on. So, and some professors have their own ideas, and then just they want their student to work on that exact same thing. Then yeah, so that can vary, but still in academia, I think, but in industry you have some like definite problems, and then you need to come up with solutions for those. Or sometimes you can also like there is no problem, but you can also come up with ideas. But so that's another. But yeah, so but still you have to, how to say, uh, it's not kind of very open-ended. Like you cannot say, oh, I can use the ResNet here in the phone. That's not possible. But in academia, you can do that because that's not a constraint. So in academia, I think the focus is more about finding a new method that is capable of solving a problem, right? And in industry, the focus is more on finding a solution that always works and never fails. So in academia, for example, you might want to use a model or like try on it like a data set that is like not very that is not very big, that does not cover a lot of scenarios. So for example, let's say a handwritten digit AI you are making identification for that. So you can probably use a small data set and just get a good accuracy, and you are done with that. You tell the world with papers that your method is good. That's it. But that's what people will evaluate you on. But in industry, you need to make sure that whatever you made, it works everywhere. So that's, I think, actually a more challenge than just to make make it work on a data set. So yeah, I think there are unique challenges in academia. You have more freedom to choose like what type of approach you are going to use. But I think, again, I should not say industry. I'm more familiar with like product development industry. In product development industry, you need to also take care into like other like all these issues of like robustness, efficiency, those things. Maybe in some, I don't know, maybe some other industry that is not a requirement, but in a like a harder product, you do need to take those things into account. And yeah, and other thing I'd say, in industry you have like lots of resources always available, but I think in academia also now it is Google Colab and all this, you get like lots of or Amazon Cloud, you get lots of resources without spending a lot of money. So that's a good thing in that regard.
Yeah, sure. Yeah, I got my answer. Yeah, thanks a lot.
Yeah.
Any other question from anyone in the Zoom?
হিৰক, মোৰ এটা প্ৰশ্ন আছে, সৰু প্ৰশ্ন।
Oh, sir.
আমি যেতিয়া আমাৰ বাহিৰৰ পৃথিৱীখনৰ লগত আমাৰ ইন্টাৰেকশ্যন হয়, যেনে ধৰা আমি বস্তু এটা দেখো বা আমি বস্তু এটা কিবা এটা শুনো বা আমি কিবা এটা বস্তু স্পৰ্শ কৰোঁ, আমাৰ কিছুমান ইমোচনেল ৰিয়েকশ্যন হয়, ৰাইট? আৰু সেই ইমোচনেল ৰিয়েকশ্যন বিলাকে আমাৰ পিছৰ ডিচিশ্যন বিলাকত ইনফ্লুৱেঞ্চ কৰে। গতিকে এই যিটো ইমোচনেল ৰিয়েকশ্যন হয়, সেইটোতো এআই ট্ৰেইন কৰা হয় নেকি?
ইমোচনেল তেনেকে নহয়, এক্সপ্লিচিটলি নহয়। তো সেইটো ইমোচনটো এটা মানে এটা কমপ্লেক্স বিহেভিয়াৰ। এইটো আই থিংক এতিয়ালৈকে এটলিষ্ট সাইকলজিষ্ট বা এনেকুৱা মানে যোনে কগনিটিভ চায়েন্স যোনে এইবোৰ ষ্টাডি কৰে, সিহঁতৰ চাগে ইমানো, আৰু এআই ৰিচাৰ্চাৰ সিহঁতে লগ লাগি এনেকুৱা ডেটা ছেট মই বনোৱা দেখা নাই, বা এনেকুৱা ধৰক প্লেটফৰ্ম বনোৱা মই দেখা নাই টু ষ্টাডি ডেট। বাট আই থিংক ইট ইজ ইম্পৰ্টেণ্ট। আৰু এটা কনচিয়াছনেছ বুলিও হেৰি আছে, এটা পেৰাডাইম আছে। তো সেইটো এটা ট'টেলি ডিফাৰেণ্ট, লাইক AI is for intelligence, right? So you do not need to be intelligent to be conscious or to be emotional. Like apuni how to say that less intelligent being eta animal eta versus human, which is highly intelligent compared to like a animal like a goat, right? But still emotion it's hard to measure, like car emotion basic. So yeah, মই তেতিয়া এতিয়ালৈকে দেখা নাই যে এনেকুৱা মানে ষ্টাডি কৰিছে কোনোবাই।
Can I add something to that? I mean, I may not be very accurate regarding the question of emotion. So actually, I think I read somewhere recently that is an advantage of AI. Say, for example, in the field of law. So when a judge passes a judgment, so often there is a human bias, so which is always unmeasurable. Because, like, I mean, when a judge listens to both sides, so there is always some kind of a human bias after interacting physically. But if, I mean, there are some studies, I cannot quote directly, but if you train a system which only believes or which only takes into account data and facts, so then maybe like that's an advantage where, you know, those emotional or conscious biases can be taken care of. But I don't know much more about it. Do you know anything, Hirak?
Yeah, actually, that's a very good point. Yeah, people are actually trying to remove emotion from this training now because, for example, I talked about ChatGPT in the first lecture in the series. So it's a chatbot, AI-based chatbot that talks to human like in a human-like way. So the first version that came before ChatGPT, so because the AI is trained on like conversations between human, like in real life, the AI also captured some of those into its training, and that can lead to potential problem. It can get angry, give like angry responses. Not it's not like it can get angry. It does not get never gets angry, but it's just learned from those kind of angry responses and just repeating similar responses to new queries. So in the latest version, they actually put human into the loop, and they looked at how during training how to remove those kind of biases from like the training so that the AI is more unbiased. So in that sense, AI is we can say it kind of reflection of the training data. It's like supervised methods where training data is used. It's kind of a reflection of what is fed into it in the training data. And the only thing it is doing during training is to make an agent which is able to learn all like which can become a representative of the training data, like an expert agent that is reflective of the training data. So yeah, so there is a constant effort to like remove all those biases. And because this kind of models now train on like internet data, for example, and if you go to Facebook or any social media websites, it's like filled with like all these kinds of people like calling names or bad things or good things, all good things, bad things, everything, like in the like chat or whatever. So if you use those as your base to train this model, the model is just capture that and will behave like that. But it's not necessarily saying it gets angry. It just learned those responses and then behaving like that. So yeah, so the current effort is to remove those kind of like human biases from training so that the AI is more neutral, like Rifat said.
Thank you again. And can I add something as far as medicine is concerned, which is little unrelated to the current topic that we are discussing? So you mentioned in your talk about supervision. So
Yeah.
I mean, so there is a lot of skepticism about utility of AI in medicine. Of course, that AI had started making inroads into medicine, but it is still very much in the early stages, maybe more in the early stages as compared to other fields of science. The reason being is that the many doctors are skeptical about how you allow a computer system to make a decision, because a patient's diagnosis or treatment takes into account a lot of things, right? Not just what is fed into the AI. And every patient is different. Like, for example, when you think about a pain in the abdomen, so there can be multiple causes, and which not always the AI can give you the answer. And you have to actually see the patient to look at what exactly is the cause of pain abdomen in that particular patient and then treat accordingly. So in that, as you talked about supervision, right? So like
Yeah.
supervision of an AI model. So especially in, or not especially, for example, in medicine, so you definitely need supervision, and all the AI algorithms to be developed, you need someone to supervise, like, you know, the initial data which are fed into the algorithm. For example, you are showing those annotations of the car and tree and things like that. The same thing happens in the medicine also. You showed the radiology image of a chest X-ray, right? I mean,
Yeah.
in pathology also, like AI is in the early stage. So you basically need a pathologist or a like doctor who will annotate, who will look at the image, annotate, and feed the proper annotation into the algorithm. And then only that AI model can develop. So that is why trained supervision is sometimes very important. And moving forward, I mean, as you said, that untrained or unsupervised AI algorithms will be a challenge. And, probably that will be the future, and in medicine especially. So, I mean, it will need to be seen how it is taken by the, medical faculty without a supervised training. Because even now, when a trained person supervises development of an AI model, so it depends on how much that person is trained. And as you said about deciding between benign and malignant, you need to have, again, I mean, on top of the AI model, you need someone to supervise, right? Otherwise, that's a huge decision which you cannot leave to the AI at the present stage, right? Because that determines the future treatment, isn't it? So yeah,
yeah.
Thank you.
Yes, I agree. I don't think at this, who knows where technology leads us in like 10, 15 years. But at this stage, AI is not there yet to, for example, replace a human doctor, like a physician. But it can, in some situations, in very narrow situations, can aid as like a early diagnosis. For example, in like many rural, like very remote areas, you might not have access to a doctor, and like in many areas there is not a specialist in a particular field. Then AI can definitely give like a initial diagnosis, so that and yeah, I should not say it should always be trusted, but if, for example, an AI model is 98% accurate and it tells you that your tumor is non-benign, then you probably you can take that seriously and go to an actual doctor to look at what is going on. And from the perspective of like going for like how it might look like, I think it will all depend on the investment, honestly. Like if the companies like medical companies or such as or insurance companies, I don't know who will be interested, but if they want to, how to say, cut the cost of physician maybe to some extent, they might want to invest a lot of money into AI, like to generate like huge amounts of training data and hopefully make an AI that is as good as a physician. But who knows? As I said, it requires a lot of investment, and currently I do not see that happening anytime soon.
Hey, Hirak, I have a question. So what's the difference between like level of accuracy of supervised and unsupervised learning? And I guess it's very situation dependent, but can you give some examples? First of all, like difference of accuracy, and also like what all the situation which is ideal for supervised and unsupervised training.
Yes. So first, in terms of accuracy, for example, the ImageNet classification problem, the accuracy is about 15%, like 15% less for unsupervised at this moment. And again, it depends on the problem. For example, in image segmentation, the accuracy might not be too bad compared to supervised because it is pixel by pixel, and it's more like a geometrical problem. If there is a point between a triangle, and all the three triangles are from like the same class, from all the three vertices of the same class, it's easy to predict that the point lying inside the triangle will be of the same class. So in that sense, there is some like other cues that help in the unsupervised methods for those kind of problem. But in there are other kind of problem. For example, in robotics, they use it for depth perception or motion perception. For motion perception, there is like no supervised data. Like it is impossible for a self-driving, almost impossible, I would say, from a self-driving car data set to like label every pedestrian in the like many 100 hours of movie, or every car that appears in like so many hours of movie. So in those situations, unsupervised learning can still guide, like still help in like at least doing some initial like feature detection or feature like representation learning based on which the supervised can be used. So I'm not sure about accuracy difference in all different problems because yeah, I like do not follow like all the literature in all the problems, but for classification, yeah, it is about 10 to 15%. And your second question was about where it might be more useful. Yeah, I think for classification, what this image is, dog or cat. So that is easy to label, like you do not need an expert. But for those radiology scan, you need a doctor to actually mark those annotations. So in the first case, just classifying it requires unskilled labor and it requires less time. So it is quite easy to get lots of training data, supervised training data. But for those kind of radiology scan with a doctor, you need a doctor or expert who actually knows exactly correctly what the scan like the what is there in the scan. So in those cases, you do not have that many doctors. It's a skill the person need to do that, and it will also cost you more money and more time. So in those situations, unsupervised learning has more how to say benefit than, for example, classification where annotation is cheap.
Thank you.
I think these are the questions that we have seen online, Hirak, and I was looking at the YouTube as well as Facebook. So on Facebook, there is a comment from one of the viewers is that thanking you for the talk, that it was very interesting and easily comprehensible. And so we also from and the entire team of 15-Minute Hirak want to thank you for this excellent talk in touching such an important and difficult topic, and you have explained it in a very simple way for all of us to understand, and I hope the students found it useful. And your next talk is coming up, so this is not, you will not be the speaker, I mean the next talk on artificial intelligence series is on February 5th, as you are showing here, by Professor Jugal Kalita, and he's going to talk on natural language processing. So hope to see everyone, and thanks to all the viewers today for joining us, and thanks for your engrossing questions, and which actually improved the session much more because you have been interacting. Thank you so much, and hope to see you again next time. Thank you.
Thank you, everyone. Yeah.
Thank you, Hirak.